Okay, here we have some voltage source, voltage V, and a couple of cylinders. Now we assume this source is resistance free, okay, no internal resistance, and we assume that there is no resistance in the connecting wires, but there's resistance in a cylinder here and a cylinder here. We're going to assume, we call this cylinder 1, call this cylinder 2, we assume that the cylinders are made of the same material and they have the same length, but one is smaller in diameter, or lesser diameter would be even better, but we call it smaller diameter, okay? So the question is, which one has the greater current? Well, we reason this out from basic principles. The current is related to the speed of the electron drift. Okay, now the speed of the electron drift doesn't totally determine the current, but clearly how fast the electrons drift is going to in some way be important for figuring out how many electrons pass a given point in per unit of time. So, current's related to the speed of the electron drift, which in turn depends on the acceleration of the electrons. Remember, the electrons form a cloud, and it's not quite accurate to say this, but we can think of it as though the electrons are free to move around anywhere in the solid, but they can bounce off of other electrons and off of atoms. So they don't get very far when they're accelerated before they bounce in a direction that might well be opposite to the direction of acceleration. So even though they might experience a lot of acceleration individually, they keep bouncing back and forth and don't make a lot of progress. So the progress that they do make is the speed of the electron drift, the average progress made by an electron. So anyhow, there's an electron drift, and the speed of the electron drift depends on the acceleration of the electrons, as we've said, which is determined by what? By the electric field. Now, people wanted to say it was determined by the voltage, it was determined by one thing or another. Well, no, actually the acceleration of the electrons is determined by what? The force on the electrons. And the force on the electrons is determined by the electric field. And of course, we assume that we're familiar with that idea now, and yeah, it's still a little bit of a shaky idea for many people. So we want to really lock in those connections. Okay, well, then how do the fields compare? Well, it should be an immediate connection that the electric field, if you have a uniform electric field over a certain distance, it's equal to the voltage change in potential per unit of distance. The unit of electric field is the Newton per Coulomb or the joule per meter. So we have the same length here. Let's call that length L. The electric field is V over L. Now we reason that out a little bit because people weren't really making that connection. The potential difference is V. So the work on each charge along the length of the wire is what? It's QV, because V is the potential difference. Okay, the work done per unit charge. Okay, so the work done is QV, and I'm kind of ignoring plus and minus signs. We'll use those shortly, but just getting the drift of the, and excuse the pun because we have drift here, or the double meaning, but the drift of the argument here. Okay, so you have a QV change in potential, a change in potential of V, so the work done to move something through that potential, the work done to move a charge Q through that potential is QV. And the work, of course, is F delta S, and in this case that would be F times delta L for the length of the wire, and F delta L then is therefore equal to QV, and we get F is Q times V over L, but of course we know that the electric field is what you multiply by the charge to get the force, meaning that the electric field must be V over L. Now, there are other